Cosmological perturbations in Palatini formalism. Please, you can start.
Okay, thank you for introduction. First of all, I'd like to thank Luca and Slavan for organizing this wonderful workshop. Really amazing. This is one of the best conference I have ever joined. Thank you so much. And today, I'm going to talk about cosmological perturbation in Palatini formalism. This work is in collaboration with Mio Kubota. She's a PhD student in Ochanomizu Women University, and Kinya is a associate professor in Osaka, and Keigo is one of my PhD students. Okay. And the content of my talk is as follows. First, I'm going to give a brief introduction to the scalar-tensor theory and Palatini formalism. But Roberto has already gave a very good introduction to Palatini formalism or metric affine formalism in the first day of this workshop. So I just give a brief introduction. And the main body of my talk is cosmological perturbation in the Palatini formalism. And let me begin with Einstein gravity in Palatini formalism. And we discussed the non-minimal coupling and also the so-called Galileon models. And in fact, there are many references related to the Palatini formalism, especially in the context of the Higgs inflation very recently. But I have to omit most of them in this talk because of the no enough space. So I apologize for the omitting such references in advance. Okay. And as all of you know, inflation and dark energy are now strongly supported by observations. But very unfortunately, we have not yet identified the inflaton and the source of dark energy. So in order to identify such inflaton and the source of dark energy, it's quite useful to consider the generic models based on the scalar-tensor theory. In fact, once we have such generic models, we can constrain the models or finally to single out the true models from the observation result. This is a kind of the so-called bottom-up approach, while in the top-down approach, we will have some unique model from the ultimate theory. But unfortunately, we don't have such a model. Of course, such a top-down model is still quite attractive, but in this talk, we take a kind of bottom-up approach. Okay. So the question is that what is the most general scalar-tensor theory to accommodate inflation or dark energy? Okay. This is the question. So let me discuss how widely can we extend the scalar-tensor theory. In the past, kinetic term of inflation is often taken to be canonical. And by taking some adequate flat potential, we realize the inflations. But almost 20 years ago, Armendais-Picon et al. Proposed that a completely generic model of the so-called K inflation, which consists of the generic function of phi and x. Okay, x is the first canonical kinetic term. And plus, of course, the Einstein-Hilbert action. But of course, inflaton is not necessarily minimally coupled to gravity. Brans-Dicke theory introduces such kind of the non-minimal couplings. And recently, this non-minimal coupling is renewed interest in the context of the Higgs inflation. And FR model is also fall into this class. We can easily show the equivalence of the FR model to this non-minimal coupled models. And of course, action or Lagrangian can include a higher derivative, not only to the first derivative x, but also some higher derivative box phi or even higher. However, as all of you know, generically speaking, this higher derivative term is dangerous due to the Ostrogradski ghost. You see, just let me briefly remind the Ostrogradski theorem. So if the action, we consider some point particle which include the higher derivative terms. So action includes or Lagrangian includes not only q and q dot, but also q double. And we assume the non-degeneracy condition, which implies that del L del q double dot still depends on q double. If we admit these assumptions, equation motions becomes a fourth order differential equation motion. Okay, because this part still depends on the q double dot. Okay, and then if we take two sets of the canonical variables, in fact, this action can be recast into the equivalent actions by introducing the capital Q, which is nothing but the Q dot. Then we introduce the two canonical variables and imposing the non-degeneracy conditions. Hamiltonian is given like this one. So the point is that this small p appears linearly, and the p can take an arbitrary value plus and minus. So it means that this system is completely unstable. And if we go into the field theories, so and the force derivative systems, you see, like this one, and consider the propagators. So this is the force power of the propagator. So one of the two degree of freedom has a long kinetic sign always. This is the essential reason why ghost degree of freedom appears in the higher derivative systems. Okay. But you may wonder, this ghost is really dangerous or not? Okay. So in the bottom-up approach, there are several classes of the models. And the most famous one is the so-called EFT approach, effective field theory approach. This is the low energy effective theory after integrating out the heavy mode, you see. And in this case, this is something like a derivative expansion. So we always have a higher derivative. And apparently, according to the Ostrogradski theories, apparently ghost always appears around the cutoff scale. But of course, this higher derivatives terms just represent the presence of the heavy degree of freedoms. In fact, we can easily derive this higher derivative terms by integrating out the heavy mode from the Ricci theories. Let us consider the heavy degree of freedom and the light degree of freedom. And consider the Ricci kinetic, Ricci Lagrangian, which consists of the first derivative. I omit some irrelevant terms. And if we are interested in the energy scale, which is smaller than this heavy mass, in that case, we can easily integrate out the heavy degree of freedom, you see. So just we make a complete square, we take a complete squares, we can integrate out this heavy degree of freedoms. Then from this Ricci Lagrangians, we get a higher derivative. Okay. But this is, of course, this is just this term represents heavy degree of freedoms, presence of the heavy degree. So nothing is wrong. But please notice that this is completely okay. But as long as we are interested in the energy scale, smaller than this cutoff scale or heavy mass, this higher derivative terms must be always subdominant in comparison to the canonical term. You see, so this heavy degree higher derivative term cannot dominate the dynamics or cannot play the important role of the dynamics. But in cosmology, you see, we often introduce some phenomenological model in which the higher derivative term plays an important role to fit the observational data. So in that case, if we introduce a higher derivative terms to make the analysis consistent, we need to kill the ghost degree of freedom, you see. And in this talk, we take such a conservative approach. Okay, just if we have some ghost, we should remove even classically. Then the question is that how to obtain a higher derivative theory without ghost degree of freedom, contrary to the Ostrogradski ghost. First way is, of course, to abandon the non-degeneracy condition, which is assumed in the Ostrogradski theory. And another is just we have going to the infinite derivative theories rather than the finite derivative theories. But in the second class, as for the second class, in this conference, we have already a lot of the interesting talks. So in this talk, we confine ourselves to the first possibility. Okay. And in fact, such a degenerate case, there is a famous example, so-called Galileon theory. If the theory has a Galileon shift symmetry in flat space, we can have this kind of the 5 candidate to satisfy this Galileon shift. And interestingly, you see, this Lagrangian apparently includes a higher derivative, second order derivative terms, but the equation motion becomes exactly second order. Then no ghost appears. Okay. In fact, this is a degenerate case. And you see, then the question is that how to covariantize this flat Galilean theory to the curved spacetime. This is the question. And now if we try to include the gravity, there are two formalisms. Of course, there are many others, but now we confine ourselves to the two formalisms, so-called the metric formalism and the Palatini formalism. And here, I would like to remind you what is a Palatini formalism to stress the difference between the metric formalism and the Palatini formalism. In the metric formalism, fundamental object or independent degree of freedom is just a Riemann matrix, which determines the length. And the connection in the metric formalism is fixed a priori to be Levi-Civita connection. So this is not an independent variable, completely determined by the matrix. And it's characterized by the symmetricity and the metric compatibility, which comes from the local Lorentz frame and the invariance of the angle between parallel transport vectors. Okay. And the important point is that in metric formalism, in order to obtain the equation motions, variation of the action is taken only with respect to the matrix. Okay. We don't take a variation of the action with respect to a connection because connection is fixed a priori Levi-Civita. On the other hand, in Palatini formalism, not only Riemann matrix, but also connection are taken as an independent. Okay? It's not, connection is not confined to Levi-Civita a priori at all. And so as a result, connection is not necessarily torsion free, or I should say not symmetric, or non-metricity is imposed or taken. So, but and in general, torsion does not necessarily vanish, or in Palatini formalism, connection is not necessarily symmetric. But in this talk, for simplicity, we consider only a torsionless case. If you wish, you can extend our result to the torsion full case. But this talk, we confine ourselves to the torsionless case. And the important point is that in Palatini formalism, to obtain the equation motions, variation of the action with respect to not only a metric, but also the connection is to be taken. This is a crucial difference. So I'm not sure how much you are familiar with Palatini formalism. So as a lesson, shall we discuss what happens to Einstein gravity in Palatini formalism by assuming the torsionless condition? Okay. So this is, we consider the this kind of simple action, Einstein-Hilbert action, and matter coupled to minimally coupled to matter. Okay. And but please notice that this Riemann Ricci scalar is made of the connection and the matrix independently. And if we take a equation of motion, okay, not only with respect to not only matrix, but also the with respect to connections, we get two equations. Okay? And we can easily solve this second equation. And this is nothing but metricity. So by combining the torsionless features, in this theory, connection is fixed to be Levi-Civita. Okay, but different from metric formalism. You see, in the metric formalism, connection is a priori fixed to Levi-Civita. But in Palatini formalism, you see, connection is coincide with the Levi-Civita, but it is a result of the equation motion. Okay, this is a crucial difference. But of course, in the Einstein gravities, metric formalism and Palatini formalism give the same prediction. Okay. So now let's try to extend gravity to a scalar tensor theory in Palatini formalism. But before going to Palatini formalism, let me briefly remember the scalar tensor theory in metric formalism. And what we'd like to do is to extend this flat Galileon theory to the curved spacetime in the metric formalism and the Palatini formalism finally. Okay. But first, let me review the this Galileon extension in the metric formalism. And actually, this Galileon, flat Galileon theory was covariantized. And it was so-called the generalized Galileon theory. And these four functions completely characterize this Galileon theory in the curved space background. And at that time, you see, this theory was proposed around 10 years ago. But at that time, unfortunately, this theory was, no one knows that this theory is the most general scalar tensor theory whose equation motions are up to the second order. And this Charmosis et al.'s paper pointed out that very surprisingly, more than 40 years ago, Horndeski has already obtained such a general theory. And actually, he obtained, he presented the most general action in 4 dimensions, constructed from the metric, scalar, and their relative, but still having the second order equation. And this action he obtained is like this one. So at that time, people wondered what's the relationship between the generalized Galileon and the Horndeski models. Then Kobayashi and Yokoyama and myself shown that actually both theories are completely equivalent. So thanks to this proof of the equivalence, now many people use this action as a Horndeski theory. But original Horndeski action is apparently looks very different. Anyway, this generalized Galileon is now most general scalar tensor theories whose Euler-Lagrange equations are up to second. And in fact, many of inflation and dark energy models can be understood in a unified manner. For example, if G4 is a constant, this is nothing but Einstein equivalent actions. And if G4 includes only phi, this is a non-minimal coupling in the form of FIR, which is often used in the Higgs inflations. And even the new Higgs inflation with the G mu nu del mu phi comes from the G phi after integration by parts. Okay. And in the same paper, we discuss the cosmological perturbation of this Horndeski theory in the metric form. And we gave a quadratic action not only the scalar perturbation, but also the tensor perturbation. And the interesting point is that sound speed of the tensor perturbation or sound speed of the gravitational wave in general can deviate from unity. Okay, if G4 has a x dependence or G5 has a phi over x dependence, in that case, sound speed of the tensor perturbation is not necessarily unity. But of course, recent observation of the gravitational waves, the gamma ray burst, strongly constrain the speed of the tensor perturbations. So if this Horndeski field is responsible for dark energies, these cross paths must be ruled out. Okay. This is the situation in the Horndeski theory in the metric form. So now let us try to extend this flat Galileon action in the Palatini formalism rather than the metric formalism. Okay. So shall we begin with K L2 and L4? And please first notice that in the metric formalism, you see, if G4 includes the X dependence in addition to the phi dependence, in order to keep the second order nature of the equation motions, counter term is necessary. But you can easily show that contrary to the metric formalism, in Palatini formalism, even if G4 includes the X dependence, and even if we don't include this counter terms, equation motion is still second order and no ghost appears in general. So you may wonder that even in Palatini formalism, and if G4 has an X dependence, speed of the gravitational wave is still unity. Let me analyze this system in 3 different frames. Okay? And the first frame is just a simple. We deal with this action as it is. Calculation is a bit tedious, but most straightforward. And another frame is a so-called Einstein frame. By making the conformal transformation, you see, from some metric to the another matrix, we can reduce this non-minimal coupling to the Einstein-Hilbert actions. By Einstein frame, we say that we have a Einstein-Hilbert action, and the connection appears only in such a Einstein-Hilbert terms. And the calculation is very well known. In fact, such analysis commonly used in the literature in the context of the Higgs equation. And the final frame is the Riemann frame. We name it. As far as I know, no one discussed this kind of the frame. But what we did is that in the Palatini formalism, connection is not necessarily coincide with the Levi-Civitas, and plus some additional terms. So once we obtain such a explicit solution of the connection and insert such a connection to this action, we can rewrite this action in terms of the Levi-Civita connection. Or I should say, we can find a corresponding theory in the metric formalism. Okay. And
Masahide,
we can make, yes.
You have
yes.
5 minutes more. Yeah.
Okay, yes. Okay. And okay, so let me begin with the Jordan frame analysis. So we have only to obtain the equation motion, okay, with respect to not only metric but also the connections. And in this case, of course, if G4 is not constant, metricity is violated. So connection does not necessarily coincide with the Levi-Civita with additional terms coming from the G4s. Okay, so now we get some generic actions. So we have just part of the metric and the connections around the background solutions. And expand the action up to the quadratic order of the perturbations. In this case, lapse, shift, and the connections are completely solved. And this is just a constraint. So we can solve and insert the solution of these lapse and shift into the action. So finally, we get a quadratic action for the tensor perturbation and the scalar perturbation. And we can confirm that the gravitational speed is shown to be unity. Okay? And move on to the Einstein frame. So we can make a conformal transformation like that. So different from the metric formalism, relation between the Ricci tensor is very simple. And so we get Einstein frame action. Okay? And this action is nothing but the KSN action and Einstein-Hilbert action with respect to this new matrix. So even in the Palatini formalism, in this Einstein frame, connection is shown to be equal to the Levi-Civita, but with respect to this new matrix. So by using the standard result of the Einstein frame analysis, we have again shown that the tensor perturbation, quadratic action of the tensor perturbation and the scalar perturbation. And of course, the tensor sound speed is shown to be unity. Okay. And finally, Riemann frame. As I told you before, in this case, connection is just a sum of the Levi-Civita plus some additional. So once we insert this generic solution of the connection to this action, we can easily rewrite this action in terms of the Levi-Civita connection. You see, so this Jordan frame action in the Palatini formalism is equivalent to this action in the metric formalism. And this action reduced to the so-called dosed action in the metric formalism. And we can easily show that the quadratic action for such a dosed action shown to coincide with those in the Jordan frame. So quadratic action for the tensor perturbation and the scalar perturbation in 3 different frames are obtained and also shown to be the same, of course. And the important point is even if G4 has X dependence, in Palatini formalism, speed of the gravitation will be unity. This is sharp contrast with the case of the metric formalism. So finally, just let me briefly discuss the Galilean action in Palatini formalism. Okay. Just 5 minutes or so. You see. And in metric formalism, you see, first, please notice that this box phi is uniquely determined thanks to the metricities. We can rewrite in this way, many ways, in this box phi, but thanks to the metric formalism, all of these expressions are completely equivalent. Okay. And this box phi terms has nothing to do with the speed of the gravitational wave in metric formalism. Actually, from the quadratic action for the tensor perturbations, you see, these two parts does not include G3 at all. So even if we take any form of G3s, speed of the sound velocity is not affected at all. This is a metric form result. But once we consider this box phi in Palatini formalism, this term is not uniquely determined at all because we don't have a metricity. So just the position of the inverse matrix, you see, we have a completely different expression of the box phi. But very fortunately, we find that there are only 10 essentially 10 different types of these forms. And schematically speaking, just we have this kind of combinations. See? And this action has in general no Einstein frame. And in general, Ostrogradski mode, different from the metric formalism. And tensor sound speed can deviate from unity. But very interestingly, if we remove the ghost degree of freedom by suitable choice of these combinations, this model reduced to the Dost model in metric formalism with speed of the gravitational wave being unity. Okay. Generically, in this model, the speed of the gravitational wave can deviate from unity. But once we remove ghosty degree of freedom, speed of the gravitational wave reduced to unity. And then it is completely safe, even if this field plays a role of the quintessence of dark energy. So let me summarize my talk. We consider the Palatini formalism, in which the variation of the action is taken with respect to not only metric, but also connection. And we consider the case of the non-minimal coupling of the scalar field and discuss the cosmological perturbation, yielding the quadratic action in 3 different frames. And finally, of course, three different frame, analysis 3 different frame is the same. And the sound speed of a gravitational wave is shown to be unity, even in the Palatini formalism, if xg4 includes x dependence. Okay? And we classify the so-called Galileon action or L3 terms in Palatini formalism, and found that there are essentially 2 different terms. And in general, these terms lead to the ghosty degree of freedom and the deviation from unity of the sound speed of the gravitational wave. But once we eliminate such a ghost degree of freedom, sound speed of the gravitational wave become unity, which coincide with that in the metric formalism, still serve as the dark energy. Thank you very much.
Thank you very much, Masahide, for a very nice talk. We have time for quick couple of questions, very quick, please. First one, James Booth.
Yeah, thank you very much for the nice talk. I have a small comment and a question. And first yes. Comment is about this name, Palatini formalism. Of course, it's somehow a misnomer, right? Because in his paper in 1919, I think this Italian paper, it's just the chain rule. So there's a delta of the variation, delta of the connection, but of course it's not really So it was made up by other people like Illy, Cartan, and others, and Einstein in the 20s, right? Yeah. So that was just the comment. But my question is this. So when you consider the connection as an independent variable, then you don't have Riemannian curvature, but you also have, like you mentioned, you have torsion and non-metricity. And these are not just tensor fields on a Riemannian manifold, right? But these are geometric objects because they enter the Bianchi identities and those kind of things. So my question is this: when you consider the gravitational action, you have the Ricci scalar from the Einstein part, but then why don't you add the invariance you can construct from torsion and curvature as well? So you could add at the leading order, you could add a torsion square, you could add curvature square, and you can add non-metricity square, right? This is just like F mu nu square in abelian or non-abelian gauge theories. So
yes.
why don't
of course, if you wish, you can add. Yeah, and in fact, very unfortunately, we have not yet obtained the most general theory in the context of the Palatini formalism. So probably if we try to consider such a theory, we need to include the terms you mentioned.
Yeah, because it's interesting in the cosmological setting, right?
Because yeah. So I agree. Just in this talk, we confine ourselves to the, in some sense, minimal extension from the flat Galileon.
My argument is that maybe it's too minimal, right? Because you are no longer in a Riemannian geometry, but you are in a geometry that is not that has more geometric properties, right? So if you limit yourself to that Lagrangian, maybe you cut out too much. That's just my concern.
Okay. Yeah. Of course, we can add. Yeah. So shall we discuss? Shall we work on that? Yeah. This is just we never mentioned that this is general or generic or something. Even G3, no one considers this type of the actions. You see, only very limited action is considered. You see, only this term is considered, and just we extend. And of course, we can extend more. We need to extend more. I agree. I totally agree with you.
And we have another question from Philip. Please be quick, please.
Yes, so good morning, Masahide. That's very interesting approach. I wanted to make a comment on your talk, but since Jen's raised the issue, the generalized connection is not a general coordinate tensor. Because in the end, if it contains the Levi-Civita piece, that Levi-Civita piece itself is not a general coordinate tensor. In fact, you must have the general connection transform the same way as the Levi-Civita connection transforms, and any other piece that you add on like torsion that piece has to be a general coordinate tensor. And the whole point of Riemann is you can build the Riemann tensor out of the connection, which itself is not a general coordinate tensor, and yet the Riemann tensor still is. Therefore, you can't just add in additional terms depending on the connection unless you find combinations that give you a general coordinate scalar action. Now, why I mention this is because the torsion is separate. It itself, the antisymmetric piece of the connection, even in the Palatini case, the antisymmetric piece is still a general coordinate tensor. And I wanted, that's my response to Jen's. Now I wanted to comment on what I was going to comment to you, but also to Roberto from his talk on the very first day, but I was never called upon to comment on it. And that is, I don't think you need to drop the torsion because the torsion takes care of itself. And let me explain why. If you start out not with the metric, but start out with the fermion equation, the Fermion-Dirac action, and you put in the torsion as part of the spin connection, then Ilya Shapiro showed that it finishes up being an axial vector field. And that axial vector field, when you then integrate out of the fermions, gives you a separate G mu nu, analog of F mu nu, but for the axial vector. And the Riemann piece that you obtain only depends on Levi-Civita and not on the torsion. So actually, the torsion can hide itself. You can have it from the beginning in the theory, but it doesn't finish up in the eventual Riemann tensor. So your result actually is okay. It would have not changed if you had introduced the torsion. You would still have this axial vector field, but the only thing we know to do with that is to make it heavy by the Higgs mechanism. Otherwise, weak interactions would be chiral. So that would be okay. So I don't think you really need to drop the torsion. Because I don't think it's going to, in the end, ever appear inside the Riemann tensor.
Some part I agree and some part I don't agree. As far as I understand, in case of the L2 and L4, if we confine up to the L2 and L4, even if we don't assume the torsionless conditions, you see, just Levi-Civita has some degree of freedom, so-called the projective symmetry. And once we fix the gauge, it's reduced to the torsionless case. But if we introduce, in case of the L3, maybe our result is not too generic. I mean, if we introduce a torsion, result might be changed. Yeah. So in general, yeah, L2 and L, in case of the L2 and L4, even if we introduce torsion, result is still robust. But for G3, as far as I understand, if we include torsion, result might be changed. This is my answer, and I'm not sure this is the answer to your question or comment.
It's a fair answer. My point is,
maybe if we can differ the.
I live in a world where fermions are the only thing that matter. And whatever I get from the fermion spin connection, that's what I should use in the geometry.
But it depends on your gravitational action, right? It depends on
sorry for interruption. Can we postpone the discussion? Postpone it to discussion session, because we are already running late. Sorry, but we will start again in the discussion session.